Among the countless stars and galaxies, a few cosmic objects stand as titans. They are monsters of energy, mass, and magnetic fury. The universe is not a quiet place. Behind the peaceful sparkle of stars on a clear night lies a realm of unimaginable violence. Out there in the vast darkness between worlds exist objects so extreme they defy our understanding of physics. These are nature's ultimate creations, born from chaos, forged in fire, and wielding forces that could tear apart solar systems in seconds. Every night, light from these cosmic beasts reaches our planet. Some of it has traveled for billions of years, carrying secrets from the edge of time itself. What stories does this ancient light tell? What warnings does it bring? At the heart of nearly every galaxy lurks a monster that bends the fabric of space and time. These are black holes, regions where gravity has won its final victory. Nothing escapes them, not even light itself. They are perfect traps. They are invisible hunters that grow by devouring everything around them. The largest ones, called supermassive black holes, weigh as much as billions of suns. They are the dark engines that power entire galaxies, yet we cannot see them directly. We only witness their terrible effects on everything nearby. Stars are torn apart. Matter is heated to millions of degrees. Space itself is twisted into impossible shapes. Then there are the stars. Not the gentle sun that warms our planet, but the true giants. Blue supergiants burn with such ferocity that they live fast and die young, exhausting their fuel in mere millions of years. These stellar furnaces forge the heavy elements that make up our world, the iron in our blood, the calcium in our bones. When they die, they do not go quietly. They explode with the brightness of entire galaxies, seeding space with the building blocks of future worlds. From the ashes of these dying giants come pulsars, cosmic lighthouses spinning hundreds of times per second. Imagine a city-sized sphere of matter so dense that a teaspoon of it would weigh as much as Mount Everest. These are neutron stars, the collapsed cores of massive suns spinning so fast they create beams of radiation that sweep across space like searchlights. Each rotation is timed with such precision that they rival our best atomic clocks. They are the universe's metronomes, keeping perfect time across the cosmos. But even pulsars pale before their violent cousins, magnetars. These are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. Their magnetism is so intense it would dissolve you from 1,000 miles away, pulling apart the very atoms of your body. When magnetars quake, they release more energy in a fraction of a second than our sun produces in 100,000 years. These starquakes send waves of gamma radiation racing across the universe, briefly outshining everything around them. At the edge of the observable universe shine the quasars, the brightest sustained sources of light in existence. These ancient beacons are powered by supermassive black holes, feeding on enormous clouds of gas and dust. As matter spirals toward its doom, it heats up and glows with the light of trillions of stars. Quasars are so luminous they can be seen from the opposite end of the universe 13 billion light-years away. They are glimpses into the cosmic past, showing us how violent the early universe truly was. And then there are the galaxies themselves, vast cities of stars. Each contains hundreds of billions of suns, along with all their planets, moons, and mysteries. Some galaxies collide in slow-motion dances that last hundreds of millions of years. Their gravitational embrace triggers the birth of new stars and feeds the giant black holes at their centers. The largest galaxies are true titans, containing over 1 trillion stars and spanning hundreds of thousands of light-years across. Each of these cosmic giants represents a different phase of power. Each pushes the laws of physics to their breaking point. They are the universe at its most extreme, its most beautiful, and its most terrifying. So we must ask, among all these titans, The black holes, the pulsars, the magnetars, the quasars, the supergiants, and the galaxies, which reign supreme. What is the most powerful object the universe can create? The answer begins 5.7 billion light-years from Earth, in a place where gravity has become a god. Phoenix A sits at the center of the Phoenix Cluster, one of the most massive gatherings of galaxies ever discovered. This is not just another black hole, this is something that shouldn't exist. It is a gravitational anomaly so large that astronomers had to check their calculations multiple times before believing what they were seeing. 100 billion times the mass of our Sun. Let that number sink in. Our entire Milky Way galaxy, with its hundreds of billions of stars, weighs about 1 trillion solar masses. Phoenix A alone contains 1/10 of that mass compressed into a region of absolute darkness. This single object outweighs many entire galaxies. The event horizon, the point of no return around a black hole, normally spans a few million miles for typical supermassive black holes. Phoenix A's event horizon stretches across 390 billion miles. To understand this scale, imagine traveling at the speed of light. It would take you over 36 hours just to circle this monster once. Our entire solar system from the Sun to the orbit of Pluto could fit inside Phoenix A's event horizon with room to spare. In fact, you could fit dozens of solar systems side by side within this sphere of darkness. But Phoenix A is not sleeping, it feeds. The black hole sits within a galaxy that blazes with unusual brightness. Every year, this galaxy gives birth to about 740 new stars, a rate almost unheard of in the modern universe. Most galaxies today, including our own produce, only a handful of stars annually. Something extraordinary is happening here, and Phoenix A is the conductor of this cosmic orchestra. Around the black hole swirls an accretion disk, a whirlpool of doomed matter spiraling toward oblivion. This is not a gentle process. As gas, dust, and torn-apart stars fall inward, they accelerate to significant fractions of light speed. The material becomes so compressed and heated that it glows with the intensity of hundreds of billions of stars. Temperatures in the inner accretion disk reach hundreds of millions of degrees. This is hot enough to emit powerful X-rays that we detect from Earth, despite the vast distance. The disk itself is structured like a cosmic hurricane. The inner regions spin faster than the outer regions, creating friction that generates tremendous heat. Matter doesn't simply fall straight into Phoenix A. It spirals inward, gradually losing energy through radiation. A single particle of gas might orbit the black hole millions of times before finally crossing the event horizon. Its death spiral lasts for thousands of years. As matter falls toward Phoenix A, something remarkable happens. Not all of it is consumed. The intense magnetic fields threading through the accretion disk channel some of the infalling material into jets. These are beams of particles accelerated to nearly light speed and shot out from the black hole's poles. These jets extend for millions of light years into space, carving vast cavities in the surrounding gas clouds. The energy in these jets is almost incomprehensible, equivalent to the total energy output of trillions of stars. The Phoenix Cluster itself tells the story of how this monster grew. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies swimming in a sea of superheated gas. The Phoenix Cluster is among the most massive ever found, and at its heart, Phoenix A has been feeding for billions of years. In the early universe, black holes grew rapidly through two methods. They consumed gas, and they merged with other black holes. Phoenix A appears to have excelled at both. The cluster's enormous gravity pulls in rivers of gas from the surrounding cosmos. This gas flows toward the center where Phoenix A awaits. Unlike smaller black holes that might struggle to capture material efficiently, Phoenix A's immense gravity ensures a steady food supply, but gas alone cannot explain Phoenix A's enormous mass. This titan has likely consumed other black holes, perhaps thousands of them. When galaxies collide within the cluster, their central black holes eventually spiral toward each other and merge. Each merger adds mass to the victor. Phoenix A sits at the bottom of a gravitational well so deep. Over cosmic time, it has inevitably drawn in and absorbed countless smaller black holes from galaxies that ventured too close. The environment around Phoenix A is unlike anywhere else in the known universe. The galaxy hosting this monster shows signs of extreme activity. Vast bubbles of superheated gas, each larger than entire galaxies, have been blown into the surrounding cluster by the black hole's jets. These cavities in the hot gas glow in X-ray light. This reveals the tremendous energy Phoenix A has pumped into its surroundings over millions of years. The cooling gas in the cluster core presents a puzzle. Normally, hot gas in galaxy clusters should cool and condense, forming new stars. But Phoenix A's jets reheat this gas, preventing it from cooling too much. It's a delicate balance. The black hole regulates star formation not just in its host galaxy, but in neighboring galaxies as well. Phoenix A is the thermostat for a region of space containing thousands of galaxies. Could Phoenix A devour entire galaxies? The physics suggests yes, given enough time. Galaxies within the Phoenix cluster move through space at hundreds of miles per second, held in orbit by the cluster's combined gravity. Occasionally, these orbits bring galaxies close to the cluster center, where Phoenix A lurks. When a smaller galaxy passes too close, tidal forces begin to tear it apart. This is the same phenomenon that causes ocean tides on Earth. The process starts subtly. Stars on the side of the galaxy closer to Phoenix feel stronger gravity than stars on the far side. This difference stretches the galaxy, pulling it into an elongated shape. As the galaxy draws nearer, the stretching intensifies. Eventually, stars begin to be pulled away, creating long streams of stellar material called tidal tails. But Phoenix A doesn't need to swallow stars directly to destroy a galaxy. Its gravitational influence disrupts the orbits of stars within the approaching galaxy. It flings some into intergalactic space, while sending others plummeting toward the cluster's center. The galaxy's gas, the raw material for future star formation, is stripped away even more easily. Ram pressure from the cluster's hot gas combines with Phoenix A's gravity to leave the galaxy quenched. This means it is unable to form new stars. Over millions of years, the galaxy dissolves. Its stars disperse throughout the cluster, many eventually finding their way into Phoenix A's host galaxy. The gas becomes part of the cluster's hot atmosphere. Some of it eventually cools and falls toward Phoenix A to feed its accretion disk. In this way, Phoenix A grows not just by direct consumption, but by orchestrating the slow dissolution of entire stellar systems. Current observations show several smaller galaxies in the Phoenix cluster displaying signs of disruption. Long streams of stars stretch between galaxies, marking the paths of past encounters. These are the scars left by Phoenix A's gravitational influence. They are evidence of galaxies being slowly torn apart and absorbed. The most disturbing aspect of Phoenix A is that it continues to grow. Measurements of the gas flowing toward the cluster center suggest that Phoenix A gains millions of solar masses each year. At this rate, it doubles its already staggering mass every few billion years. There appears to be no upper limit to how large it can become. The radiation from Phoenix A's accretion disk creates a zone of influence extending for millions of light years. Within this zone, the black hole's energy output affects everything: heating, gas, triggering or suppressing star formation, and even influencing chemical evolution. Phoenix A doesn't just occupy space. It dominates and reshapes an entire region of the universe. Deep in the cluster's core, time itself behaves strangely near Phoenix A. The black hole's immense mass warps spacetime so severely that time passes differently at various distances from the event horizon. If you could somehow survive near the event horizon, you would age more slowly than someone farther away. From your perspective, near the black hole, the outside universe would appear to speed up. Stars would live and die in what seemed like moments. The X-ray telescopes that study Phoenix A reveal constant variation in its brightness. The accretion disk flickers and flares as clumps of matter make their final plunge past the event horizon. Each flare represents the death of something, perhaps a star torn apart or a massive cloud of gas finally succumbing to gravity. These variations tell us that Phoenix A is actively feeding right now 5.7 billion years in the past, the time its light took to reach us. What Phoenix A represents is gravity's ultimate victory. It is a region where one of nature's fundamental forces has overwhelmed all others. No amount of pressure, no nuclear fusion, no electromagnetic repulsion can resist the pull beyond the event horizon. It is a one-way gate out of our universe, a place where the known laws of physics cease to function as we understand them. While Phoenix A demonstrates gravity's silent dominance, 12 billion light-years away, something far more violent burns. It is a cosmic furnace that makes Phoenix A look dim by comparison. The quasar S50014+81 defies comprehension. Where Phoenix A whispers with gravity, the quasar screams with radiation. This is luminosity taken to its absolute extreme. 300 trillion times brighter than our Sun. If this quasar were placed 280 astronomical units from Earth, about 7 times the distance to Pluto, it would appear as bright as our Sun. But it sits 12 billion light-years away, and we can still see it. This quasar belongs to the universe's violent youth. The light we see from the quasar left when the universe was less than 2 billion years old. This was a time when cosmic violence was the norm rather than the exception. Quasars are time machines, showing us an era when supermassive black holes grew with terrifying speed. They fed on vast reservoirs of gas that no longer exist in today's calmer universe. At the heart of the quasar lies a black hole of 40 billion solar masses. This is smaller than Phoenix A, yet it somehow generates far more energy. This paradox reveals a fundamental truth about black holes. Size alone doesn't determine power. What matters is how fast they feed, and the quasar feeds at nearly the maximum rate physics allows. The difference between a sleeping giant like Phoenix A and a raging quasar lies in their food supply. The quasar exists in a galaxy drowning in gas. Every second, matter equivalent to 4,000 suns pours into the black hole's accretion disk. This material doesn't fall quietly into darkness. It dies in the brightest way possible. As gas spirals toward the black hole, it forms a disk that spans light years across. The inner edge of this disk reaches temperatures of billions of degrees, hotter than the center of any star. At these temperatures, matter doesn't just glow, it transforms. Atoms are stripped of their electrons. Protons and neutrons break apart. The disk becomes a soup of fundamental particles radiating across the entire electromagnetic spectrum, from radio waves to gamma rays. The efficiency of this process borders on the miraculous. When matter falls into the quasar, up to 40% of its mass converts directly into energy. This happens through friction and gravitational compression before it crosses the event horizon. By comparison, nuclear fusion in stars converts less than 1% of mass into energy. The quasar is the universe's most efficient engine, extracting more energy from matter than any other known process. This energy doesn't radiate uniformly in all directions. The spinning accretion disk and the black hole's magnetic field create a natural focusing system. Like a lighthouse beam, much of the radiation emerges in two opposing jets perpendicular to the disk. These jets punch through the surrounding galaxy and extend into intergalactic space. They carry energy across millions of light years. The host galaxy of the quasar, if we can even call it that, is completely overwhelmed by its central monster. The quasar's light drowns out the combined glow of hundreds of billions of stars. From our perspective on Earth, we see only the brilliant point of the quasar itself. The galaxy around it is invisible, lost in the glare like a candle held in front of a searchlight. But we can infer the galaxy's presence through other means. The spectrum of the quasar's light reveals surrounding clouds of gas. Some are falling inward, and some are blown outward by radiation pressure. These clouds move at thousands of miles per second, their velocities traced by the Doppler shift of their spectral lines. The galaxy is there, but it exists in the shadow of its own center. The radiation from the quasar extends far beyond visible light. Radio telescopes detect powerful emissions from electrons spiraling in magnetic fields. X-ray observatories see the ultra-hot corona above the accretion disk. Gamma-ray detectors occasionally catch flares when the jets point directly at Earth. Each wavelength tells a different part of the story, revealing layers of violence stacked upon each other. The broad line region around the quasar spans several light years. It is filled with clouds of gas moving at up to 10,000 miles per second. These clouds glow from the intense ultraviolet radiation flooding out of the accretion disk. The atoms in these clouds are constantly being ionized and recombining, creating a forest of emission lines in the quasar's spectrum. By measuring these lines, astronomers can weigh the black hole and clock the speed of material orbiting it. Further out, the narrow line region extends for thousands of light years. Here, gas clouds move more slowly, but they still glow from the quasar's radiation. This region marks the boundary between the quasar's direct influence and the normal interstellar medium of the galaxy. Beyond this point, the radiation weakens enough that normal stars can exist, though normal is relative when living next to such a monster. The wind from the quasar is perhaps its most destructive feature. Radiation pressure from the quasar accelerates gas outward at speeds approaching 10% of light speed. This wind carries away more mass than the black hole consumes, clearing out the galaxy's gas reserves. It's a self-limiting process. Eventually, the quasar will exhaust its food supply and fade, but for now the quasar burns at full power. The question of life becomes urgent when considering the quasar's output. Could anything survive in a galaxy hosting such a monster? Could life exist even in neighboring galaxies? The numbers are sobering. Within the quasar's host galaxy, the radiation field would be lethal to any form of life as we know it. The constant bombardment of high-energy photons would shatter DNA and break apart organic molecules. It would also strip away planetary atmospheres. Even on the night side of planets, the radiation reflecting off interstellar gas would deliver killing doses. Water, the foundation of life as we understand it, would be dissociated into hydrogen and oxygen by the intense ultraviolet light. These elements would then be ionized and blown away by the quasar wind. Rocky planets would see their surfaces baked and their atmospheres eroded. Gas giant planets would have their outer layers stripped away, leaving only their cores. But the danger extends beyond the host galaxy. The quasar's jets carry deadly radiation across intergalactic space. If Earth were in the path of one of these jets, even from 1,000,000 light years away, the results would be catastrophic. The radiation would destroy our ozone layer within months. Ultraviolet light from the sun would then reach the surface, unfiltered, causing mass extinctions. The upper atmosphere would be ionized, creating a cascade of chemical reactions that would further damage the protective layers around our planet. Even planets not directly in the jet's path would suffer. The broad radiation field from the quasar extends outward in a sphere. It weakens with distance but never truly disappears. Calculations suggest that within a radius of several million light-years, the background radiation level would be high enough to significantly increase mutation rates. It would also increase cancer incidence in any complex organisms. The most insidious effect might be on stellar nurseries. Regions of space where new stars and planets form require cold, dense molecular clouds. The radiation from the quasar heats and ionizes these clouds, preventing them from collapsing. In essence, the quasar sterilizes not just existing life, but prevents new life from ever beginning. It creates a dead zone around itself where planetary systems cannot form. The timescales involved make the situation even more dire. The quasar has been burning at this intensity for millions of years and could continue for millions more. Any civilization developing in a nearby galaxy would face constant bombardment throughout its entire evolutionary history. The radiation would be a permanent feature of their sky, a deadly rain that never stops. Consider what this means for the distribution of life in the universe. Around every quasar, there exists a zone of death, a region where life cannot arise or survive. During the quasar era of the early universe, when objects like this quasar were common, vast regions of space would have been permanently sterilized. Life might have been confined to quiet backwaters far from the centers of galaxies where quasars burned. The chemical enrichment from the quasar adds another layer to this story. The quasar wind carries heavy elements, forged in the accretion disk, out into intergalactic space. These elements, carbon, oxygen, iron, are essential for life, yet they're being dispersed by the very process that makes the region uninhabitable. It's a cosmic irony. The quasar spreads the ingredients for life while simultaneously making life impossible. From the ancient violence of quasars, we return closer to home, to our own galaxy, where a different kind of monster exists. It is not one of gravity or blinding radiation, but of pure, overwhelming size. Scuti defies our sense of scale. This star is so large that light itself takes hours to cross from one side to the other. Located 9,500 light-years from Earth in the constellation Scutum Uy, Scuti is a red hypergiant. It is a star that has swollen to dimensions that shouldn't be possible. Its radius extends 1,700 times farther than our Sun's. Numbers fail to convey what this means. If Scuti replaced our Sun, its surface would extend beyond the orbit of Jupiter. Mercury, Venus, Earth, Mars, and Jupiter would all orbit inside the star itself. Saturn would barely escape skimming just above the star's bloated photosphere. The inner solar system wouldn't just be vaporized. It would cease to exist as separate entities, becoming part of the star's outer layers. But Scuti's surface is nothing like our Sun's. Where our Sun has a relatively sharp boundary between its interior and the vacuum of space Scuti fades gradually. Its outer layers are so tenuous they're closer to a hot vacuum than what we would consider stellar material. The density at Scuti's visible surface is less than the air at Earth's surface. You could fly a spacecraft through the star's outer atmosphere, though it would be instantly vaporized by the temperature. This ethereal surface hides internal violence on a scale that dwarfs anything in our solar system. Inside Scuti convection cells larger than Earth's orbit rise and fall. These are columns of superheated gas, each carrying more energy than our Sun produces in a year. They rise from the star's depths at speeds of hundreds of miles per second, cool slightly at the surface, then plunge back down to be reheated. Each convection cell is a world unto itself. The rising columns glow white-hot, while the descending material is darker and cooler. From Earth we see these patterns as variations in the star's brightness. Scuti pulsates irregularly. Its light output varies as massive convection cells break through the surface and subside. These pulsations occur on timescales of months to years. Each one involves the movement of more mass than exists in our entire solar system. The temperature at UY Scuti's surface is relatively cool by stellar standards, about 3,300 degrees Celsius. This is compared to our Sun's 5,500. This low temperature is why the star appears red, but this coolness is deceptive. The total energy output from UY Scuti is 340,000 times greater than our Sun. Every second UY Scuti radiates enough energy to power a human civilization for billions of years. This tremendous luminosity comes at a price. UY Scuti is burning through its nuclear fuel at a catastrophic rate. While our Sun will shine steadily for 10 billion years, UY Scuti's life is measured in mere millions. The star is already near death, though near, in cosmic terms, still means hundreds of thousands of years. Inside UY Scuti's core, the situation is extreme beyond imagination. The temperature exceeds 300 million degrees. This is hot enough to fuse not just hydrogen into helium, but helium into carbon, carbon into oxygen, and oxygen into silicon. The star has become a factory for heavy elements. Its core resembles an onion with different layers fusing different elements simultaneously. The radiation pressure from these fusion reactions is what holds UY Scuti up against its own gravity, but it's a precarious balance. The star constantly teeters on the edge of collapse. Small changes in the fusion rate cause the entire star to expand or contract by distances greater than Earth's orbit. These oscillations send shock waves through the star's interior, each one powerful enough to destroy planets. UY Scuti's stellar wind is a hurricane that never stops. The star loses mass at a rate of about 1 Earth mass every year, blown away by its own radiation. This wind extends for light years around the star, creating a bubble of hot gas in interstellar space. Any planets that might have once orbited UY Scuti have long since been stripped of their atmospheres and eroded away by this constant gale. The composition of UY Scuti tells the story of its evolution. Spectroscopic observations reveal an atmosphere enriched with heavy elements, carbon, oxygen, and nitrogen, that have been dredged up from the star's interior by convection. These elements form complex molecules in the star's cool outer layers, titanium oxide, water vapor, and even simple organic compounds. UY Scuti is a chemical factory operating on a stellar scale. The star's magnetic field adds another layer of complexity. While much weaker than the fields around neutron stars or magnetars, UY Scuti's magnetic field is still powerful. It is powerful enough to channel the stellar wind and create hotspots on the surface. These magnetic structures are constantly being created and destroyed by the roiling convection. This leads to unpredictable variations in the star's spectrum and brightness. Surrounding UY Scuti is a vast shell of gas and dust, material the star has shed over thousands of years. This circumstellar envelope extends for several light years and glows with infrared light. The dust grains in this envelope are factories themselves, sites where complex molecules form from the elements expelled by the star. Some of these molecules will eventually be incorporated into new planets around future stars. The fate awaiting UY Scuti depends on its exact mass, which remains uncertain due to the difficulty of weighing such a distant variable star. If UY Scuti is less than 20 times the Sun's mass, which seems likely, it will end its life as a supernova. But this won't be an ordinary stellar explosion. When fusion finally stops in UY Scuti's core, nothing will remain to hold the star up against gravity. The core will collapse in less than a second. It will reach densities where protons and electrons are crushed together into neutrons. This collapse will release a flood of neutrinos, ghostly particles that rarely interact with matter but carry away enormous energy. The neutrino burst from UY Scuti's death will briefly outshine the entire visible universe in neutrino light. The collapsing core will rebound, sending a shock wave outward through the star. This shock wave will take hours to reach UY Scuti's bloated surface, but when it does, the results will be spectacular. The star's outer layers will be ejected at speeds of thousands of miles per second. For weeks, the supernova will shine with the light of billions of suns visible from neighboring galaxies. But there's another possibility. If UY Scuti is more massive than current estimates suggest, it could die in an even more violent event, a hypernova. In this scenario, the collapsing core forms a black hole surrounded by an accretion disk of infalling stellar material. Jets of matter accelerated to near light speed would punch through the star's poles. This would create gamma-ray bursts that could be detected from across the universe. The energy released in a hypernova exceeds that of ordinary supernovas by factors of hundreds. The explosion would completely unbind UY Scuti, leaving no remnant except a black hole. The ejected material would be accelerated to significant fractions of light speed, creating a supernova remnant that would glow for thousands of years. Either way, UY Scuti's death will enrich the surrounding space with heavy elements. These elements include iron forged in the star's final moments and gold and uranium created in the explosion itself. These elements will drift through space for millions of years before being incorporated into new stars and planets. Every atom of these elements on Earth came from a dying star. The shockwave from UY Scuti's explosion will compress nearby gas clouds, triggering the formation of new stars. In this way, the death of hypergiants like UY Scuti drives the continued evolution of galaxies. They are stellar phoenixes, their deaths giving birth to new generations of stars. Currently, UY Scuti shows signs of increasing instability. Observations over the past century reveal growing irregularity in its pulsations. The star occasionally experiences massive eruptions, ejecting shells of gas at high velocity. These events might be precursors to the final collapse, though predicting exactly when a star will explode remains beyond our capability. The surface gravity on UY Scuti is about 100,000 times weaker than on Earth, despite the star's enormous mass. This is due to the vast distance between the surface and the center of mass. If you could somehow stand on UY Scuti's surface, you would weigh less than a gram, but you would also be immediately vaporized and blown away by the stellar wind. The low surface gravity means UY Scuti barely holds onto its outer layers. The star exists in a state of near dissolution. Its outer envelope is so loosely bound that relatively small disturbances can eject massive amounts of material. Solar flares that would be minor events on our Sun can lift entire Earth masses of gas from UY Scuti's surface. Deep inside UY Scuti, time runs differently. The intense gravity near the core causes gravitational time dilation. Time passes more slowly there than at the surface. Over the star's lifetime, this effect accumulates. The core has aged days less than the surface, though both have existed for the same number of years by external clocks. The convection patterns inside UY Scuti are chaotic in the mathematical sense. Small changes in conditions can lead to vastly different outcomes. A slightly hotter bubble of gas rising from the core can trigger a cascade of effects that alter the star's brightness months later. This sensitivity to initial conditions makes UY Scuti's behavior fundamentally unpredictable beyond short timescales. Observations in different wavelengths reveal different aspects of UY Scuti. In visible light, we see the star's photosphere. In infrared, we detect the warm dust in its circumstellar envelope. Radio observations reveal molecular clouds around the star, while ultraviolet light shows hot spots where magnetic fields channel energy. Each wavelength provides a piece of the puzzle, but the complete picture remains elusive. The stellar wind from UY Scuti creates a bow shock as the star moves through space. Like a boat moving through water, the star pushes interstellar gas ahead of it. This creates a compressed region that glows in infrared light. Behind the star trails a wake of disturbed gas that will take thousands of years to settle back to equilibrium. When stars like UY Scuti finally collapse, they sometimes leave behind something that represents the opposite extreme. It is not vast and tenuous, but impossibly small and dense. In the constellation, Sagittarius, 18,000 light-years away, spins the fastest rotating object ever discovered, PSR, J1748-2446 AD. This pulsar completes 716 full rotations every second. To grasp this speed, consider that its equator moves at nearly 1/4 the speed of light. A point on its surface travels 30,000 miles in the time it takes you to blink. This object, no larger than Manhattan, spins faster than the blades of a jet engine. It spins faster than any mechanical device humans have created, approaching the theoretical limit of how fast matter can rotate without tearing itself apart. The object itself is a neutron star, the collapsed core of a massive star that exploded long ago. When a star 8 to 20 times our Sun's mass runs out of nuclear fuel, its core collapses so violently. Protons and electrons are crushed together into neutrons. What remains is a sphere of nuclear matter 12 miles across but containing more mass than our Sun. The density defies comprehension. A sugar cube-sized piece would weigh 100 million tons on Earth. But density alone doesn't explain the rotation. When the original star collapsed, it carried its rotation with it. Like an ice skater pulling in their arms to spin faster, the shrinking stellar core accelerated dramatically. A star that once rotated every few days now spins hundreds of times per second. The conservation of angular momentum, a basic law of physics, creates this cosmic dynamo. The surface gravity on this pulsar exceeds Earth's by 200 billion times. If you dropped an object from 1 meter above the surface, it would strike at 4.3 million miles per hour. The escape velocity, the speed needed to break free from the surface, approaches half the speed of light. Mountains on this neutron star, if they exist, can be no taller than a few millimeters before gravity crushes them flat. The magnetic field threading through this pulsar carries a strength 1 trillion times more powerful than Earth's. This field, spinning with the star, creates an electric generator of staggering proportions. The rotating magnetic field accelerates charged particles to near light speed. This creates beams of radiation that sweep through space like lighthouse beams. Each rotation sends a pulse of radio waves, X-rays and gamma rays across the cosmos. These beams don't emerge from the entire star, but from hotspots near the magnetic poles. As the star spins and the beams sweep past Earth, we detect regular pulses, hence the name pulsar. The timing of these pulses is so precise that they rival atomic clocks. Over years of observation, the pulse arrival times can be predicted to nanosecond accuracy. The interior of this neutron star remains one of the universe's great mysteries. The outer layer is likely solid, a crystalline lattice of atomic nuclei arranged in a grid swimming in a sea of superfluid neutrons. This crust experiences starquakes, sudden rearrangements that release more energy than our Sun produces in years. These quakes can alter the star's rotation rate, causing glitches in the otherwise perfect timing of the pulses. Deeper inside, matter exists in states impossible to create on Earth. The pressure exceeds anything in terrestrial laboratories by factors of billions. Neutrons might break down into their constituent quarks, forming exotic matter. There might be hyperons, particles containing strange quarks. The core might even contain a soup of free quarks, unbound from their usual groupings. Each possibility would affect the star's mass and rotation in measurable ways. The centrifugal force at this pulsar's equator is extraordinary. Matter there experiences an outward pull that nearly equals the inward pull of gravity. The star is oblate, flattened at the poles like Earth, but to a much greater degree. If it spun just 50% faster, centrifugal force would overcome gravity. The star would fly apart, spraying nuclear matter into space at relativistic speeds. This particular pulsar didn't achieve its incredible rotation rate alone. It's a recycled or millisecond pulsar spun up by matter stolen from a companion star. For millions of years, gas from a neighboring star spiraled onto the neutron star's surface. Each infalling particle added its angular momentum to the spin. This process, called accretion-powered spin-up, transformed an old, slow pulsar into the speed demon we observe today. The companion star that donated this matter has been reduced to a burned-out cinder. It is a brown dwarf orbiting the pulsar every 26 hours. The pulsar's radiation and particle wind continue to erode this companion, slowly vaporizing it. In a few billion years, nothing will remain but the pulsar spinning alone in space, having consumed its partner entirely. The energy output from this pulsar's rotation is enormous. As it spins, it loses rotational energy through magnetic braking. The magnetic field carries away energy, gradually slowing the spin. This energy emerges as radiation and a wind of charged particles moving at near light speed. The total power output exceeds our sun's by factors of thousands, all from an object smaller than a city. The precision of pulsar timing opens remarkable possibilities. Networks of pulsars across the sky could serve as a galactic positioning system. By measuring the arrival times of pulses from multiple pulsars, a spacecraft could determine its position anywhere in the galaxy. It could determine its position to within a few miles. This natural navigation system requires no satellites, no ground stations, just the ability to detect and time pulsar signals. Pulsars also act as laboratories for testing fundamental physics. The regular pulses pass through the warped space-time around massive objects. This allows us to test Einstein's general relativity in regimes impossible to access on Earth. Binary pulsars, where two neutron stars orbit each other, have confirmed the existence of gravitational waves decades before they were directly detected. The fastest pulsars push matter to its limits. The nuclear material at the surface must withstand stresses that would instantly vaporize any earthly substance. The magnetic field lines are so dense they affect the vacuum of space itself. They create regions where matter and antimatter spontaneously appear from nothing, only to annihilate microseconds later. The temperature at this pulsar's surface reaches millions of degrees. This is hot enough that the thermal radiation peaks in X-rays rather than visible light. But the temperature isn't uniform. The magnetic poles where particles crash into the surface glow even hotter. These hot spots, no larger than city blocks, outshine entire normal stars in X-ray light. Surrounding the pulsar is a magnetosphere, a region dominated by the magnetic field rather than gravity. This magnetosphere extends for thousands of miles, filled with electrons and positrons moving at relativistic speeds. These particles emit synchrotron radiation as they spiral along magnetic field lines. This creates a nebula of high-energy light around the pulsar. The particle wind from this pulsar creates a bubble in interstellar space, pushing back the surrounding gas and dust. Where this wind meets the interstellar medium, a shock front forms, heating gas to millions of degrees. This pulsar wind nebula glows across the electromagnetic spectrum. It is a signature of the neutron star's power, affecting space for light years around. Time itself behaves strangely near this pulsar. The intense gravity causes significant time dilation. Clocks on the surface run 30% slower than clocks far away. Combined with the rapid rotation, this creates complex relativistic effects. Different parts of the star age at different rates. The equator, moving fastest, ages slightly slower than the poles due to velocity-based time dilation. The pulsar's rotation provides a historical record written in millisecond precision. By carefully measuring how the rotation rate changes over time, astronomers can detect the gravitational influence of passing stars. They can detect the effect of the galaxy's gravitational field and even the recoil from asymmetric particle emission. The pulsar is both clock and logbook recording interactions spanning millions of years. The matter falling onto this neutron star from its companion doesn't accumulate smoothly. It builds up in a layer until the pressure and temperature trigger thermonuclear fusion. The entire surface can ignite in seconds, a runaway fusion reaction that briefly outshines the steady emission by factors of thousands. These X-ray bursts last seconds to minutes, each one releasing more energy than our Sun produces in a week. Between these dramatic bursts, the accreted matter undergoes strange transformations. The immense pressure can create exotic forms of matter: crystallized carbon, solid oxygen, metallic hydrogen. These materials, impossibly compressed, have properties unlike anything on Earth. They might be superconducting, carrying electrical current with no resistance. They might be superfluid, flowing without friction. The magnetic field lines emerging from this pulsar extend far into space, but they're not static. They twist and reconnect, releasing bursts of energy. These magnetic reconnection events accelerate particles to energies higher than any human particle accelerator can achieve. The pulsar is a natural laboratory for high-energy physics. It creates conditions that existed only in the first microseconds after the Big Bang. Navigation using pulsars wouldn't be limited to our galaxy. Each pulsar has a unique signature, its rotation period, how that period changes over time, and the shape of its pulses. A catalogue of pulsar signatures would work anywhere in the universe. A spacecraft arriving in a distant galaxy could orient itself by identifying known pulsars. It could determine both its location and the time elapsed since leaving Earth. The discovery of pulsars this fast required special techniques. Traditional radio telescopes couldn't sample fast enough to resolve individual pulses. New digital systems had to be developed capable of recording data millions of times per second. Even then, the signal processing required to extract the pulsar signal from the noise pushed computers to their limits. While the previous pulsar demonstrates nature's limits of rotation, 20,000 light-years away in the constellation Sagittarius lurks something that pushes a different boundary entirely. SGR 1000, 806-20, is a magnetar whose magnetic field represents the strongest force ever measured in the universe. This magnetar's magnetic field strength reaches 100 billion Tesla. For comparison, Earth's magnetic field measures 10 to the power of -5 Tesla. The strongest sustained magnetic fields humans can create reach about 45 Tesla. This magnetar's field exceeds our best efforts by billions of times. It creates an environment where the normal rules of matter and energy break down completely. On December 27, 2004, this magnetar reminded the universe of its power. A massive reorganization of its magnetic field, a starquake in its solid crust, released more energy in 1/10 of a second than our Sun produces in 150,000 years. The burst of gamma rays and X-rays that erupted from the magnetar was so intense. Despite originating 20,000 light-years away, it overwhelmed satellite detectors designed to study much weaker sources. When this flash of radiation reached Earth, it had traveled for 20,000 years through the vacuum of space, weakening with distance. Yet when it arrived, it was still powerful enough to ionize Earth's upper atmosphere. It created effects usually seen only during major solar storms. Radio communications were disrupted. The ionosphere, the charged layer of our atmosphere that reflects radio waves, was physically compressed by the radiation pressure. The gamma-ray flash was brighter than the full moon in gamma-ray light. This made the magnetar briefly the brightest object in Earth's sky outside our solar system, though invisible to human eyes. Spacecraft throughout the solar system detected the burst. Even satellites facing away from the source registered the flash as gamma rays bounced off the moon and planets. The energy release didn't stop with that initial flash. For minutes afterward, the magnetar rang like a bell, its solid crust vibrating from the starquake. These vibrations modulated the X-ray emission, creating a pattern that revealed the frequencies at which a neutron star naturally oscillates. Each oscillation mode corresponds to different ways the star can vibrate. Some compress the entire star, others create traveling waves around the equator. Still others twist the star's shape. To understand what triggers such events, we must examine the magnetar's structure. The magnetic field doesn't simply surround the star, it threads through it, emerging from the interior, looping through the magnetosphere, and diving back into the crust elsewhere. These field lines carry enormous stress where they emerge from or enter the surface. They exert pressure that can crack the stellar crust like tectonic plates on Earth. The crust of this magnetar is perhaps the strongest material in the universe. It is a crystalline lattice of atomic nuclei compressed to nuclear density. Yet even this extraordinarily rigid material cannot withstand the magnetic stresses indefinitely. The field slowly evolves, twisting and stretching the crust until it suddenly fractures. The energy released in these fractures powers the observed flares. Inside the magnetar, the magnetic field affects matter in ways impossible anywhere else. At field strengths above 10 billion Tesla atoms cease to exist in their normal form. The electron clouds that usually surround atomic nuclei are compressed into thin cylinders aligned with the magnetic field. Atoms become needle-shaped, thousands of times longer than they are wide. Chemistry as we know it cannot exist. The vacuum itself behaves differently in these extreme fields. Quantum mechanics predicts that empty space constantly creates virtual particle pairs, an electron and positron that appear and immediately annihilate. Near this magnetar, the magnetic field can prevent these pairs from recombining, turning virtual particles into real ones. The vacuum literally boils with particle creation. Light passing through this magnetic field doesn't travel normally. The field causes vacuum birefringence. Photons split into two polarization modes that travel at slightly different speeds. A pulse of light becomes smeared out, its polarization rotating as it propagates. This effect, predicted by quantum electrodynamics but never observed in laboratories, occurs naturally around magnetars. The surface temperature of this magnetar reaches 10 million degrees. This is hot enough that the thermal radiation peaks in X-rays, but the temperature isn't distributed evenly. The magnetic field channels heat flow, creating hot spots where field lines concentrate and cooler regions where the field is weaker. The surface resembles a patchwork of different temperatures, each patch glowing with different intensity. The magnetar's rotation once every 7.5 seconds is gradually slowing. The magnetic field acts as a brake, carrying away rotational energy. But this slowing isn't smooth. The magnetar experiences glitches, sudden speed-ups when the crust cracks and the star's shape changes slightly. After each glitch, the rotation resumes its gradual decline, but at a slightly different rate. The connection between magnetars and fast radio bursts has become increasingly clear. These mysterious flashes of radio waves lasting milliseconds but releasing enormous energy were first discovered in 2007. For years, their origin remained unknown. Then, in April 2020, a magnetar in our own galaxy produced a fast radio burst. This confirmed what many had suspected. At least some of these enigmatic signals come from magnetar flares. The mechanism likely involves the magnetosphere, the region around the magnetar dominated by its magnetic field. When magnetic field lines suddenly reconnect, they can launch clouds of plasma at relativistic speeds. As these plasma clouds plow through the surrounding magnetosphere, they generate coherent radio emission. This happens through a process similar to how pulsars create radio waves, but it is far more powerful. This magnetar sits in a unique environment. The 2004 giant flare excavated a cavity in the surrounding interstellar medium. It created a bubble of hot, low-density gas. Subsequent smaller flares maintain this cavity, keeping it clear of the dust and gas that fills most of interstellar space. The magnetar has created its own void, a region where its influence dominates over the normal interstellar environment. The X-ray spectrum from this magnetar reveals absorption lines that shouldn't exist. These lines, called proton cyclotron features, occur when protons in the magnetosphere absorb X-rays at specific energies. These energies are related to the magnetic field strength. The detection of these features provided a direct measurement of the field strength, confirming the incredible values predicted by theory. Surrounding the magnetar is a wind of particles, electrons, positrons, and ions, accelerated to nearly the speed of light by the rotating magnetic field. This wind carries away energy and angular momentum, contributing to the magnetar's spin-down. Where the wind meets the interstellar medium, it creates a pulsar wind nebula. It is, however, fainter than those around ordinary pulsars due to the magnetar's slower rotation. The magnetic field configuration around this magnetar is far from simple. Instead of a neat dipole like Earth's field, the magnetar's field is multipolar. It is a complex arrangement of magnetic poles and twisted field lines. This complexity arises from the field's origin deep in the neutron star's interior, where convection and differential rotation create a magnetic dynamo. The lifetime of a magnetar's extreme field is limited. The field gradually decays through ohmic dissipation. Electrical resistance in the star's crust slowly converts magnetic energy into heat. This decay takes about 10,000 years, making magnetars cosmic mayflies. For every active magnetar we observe, hundreds of dead ones must exist, their fields decayed to ordinary pulsar levels. During its active lifetime, this magnetar will experience hundreds of smaller flares between giant events. These smaller outbursts, releasing only as much energy as the Sun produces in years or decades, occur monthly or even weekly. Each one provides data about the magnetic field configuration and how it evolves over time. The gravitational field around this magnetar warps space-time measurably. Light passing close to the star follows curved paths, an effect called gravitational lensing. This bending is strong enough that we can see parts of the far side of the star. Its gravity bends light around itself. The combination of gravitational lensing and rapid rotation creates complex patterns in the observed X-ray emission. The 2004 flare from this magnetar may have had effects beyond Earth. Any planets within a few light years would have experienced severe atmospheric stripping. The radiation would have broken apart molecules in their upper atmospheres, allowing the constituent atoms to escape to space. Over time, repeated flares could completely erode a planet's atmosphere, leaving it a barren rock. The study of this magnetar requires special techniques. Normal X-ray detectors saturate when observing such bright sources. Scientists must use indirect methods, like watching X-rays bounce off dust clouds near the magnetar. This allows them to study its emission without overwhelming their instruments. It's like studying the sun by looking at its reflection rather than directly at it. The internal structure of this magnetar remains partly mysterious. The core might contain free quarks, hyperons, or even more exotic particles. The magnetic field affects these particles differently than normal matter. This could potentially create regions where different phases of matter coexist. The star might have layers like an onion, each composed of different exotic materials. Theoretical models suggest this magnetar formed from a star at least 30 times our Sun's mass. When this progenitor star exploded as a supernova, something unusual happened. Perhaps the core was rotating exceptionally fast, or perhaps it had an unusually strong magnetic field to begin with. The exact conditions needed to create a magnetar rather than an ordinary pulsar remain debated. The magnetic pressure inside this magnetar is comparable to the matter pressure. This means the magnetic field significantly affects the star's structure. It makes the star larger than a non-magnetic neutron star of the same mass. The field also affects the star's oscillation modes, creating unique vibration patterns. These patterns serve as fingerprints of the internal field configuration. Energy storage in this magnetar's magnetic field exceeds 10 to the 47th ergs. This is more than our Sun will produce in its entire lifetime. This energy slowly leaks out through flares and particle winds. By the time the field decays completely, the magnetar will have radiated away enormous energy. This energy will be equivalent to a significant fraction of its rest mass energy. It's easy to forget just how fast things have changed. Just 2 years ago, when we talked about the most distant galaxies, most of what we said came with a giant unspoken asterisk. We thought that we saw the very first stars that were forming. We believed that we had an idea of what the early galaxies looked like. And when it came to alien planets, we were basically guessing, tracing faint shadows and hoping for the best. Then the James Webb Space Telescope opened its golden eyes, and suddenly the asterisks started to disappear. We were not just detecting the planets anymore. We were finding the actual signs of what might be in their atmospheres. We were not squinting at the blurry dots from 13 billion years ago. We were looking at fully formed galaxies that, according to everything we thought we knew, should not have even existed yet. And that was just in the first few months. Since then, the James Webb has rewritten our understanding of the universe, one target at a time. It found ghost galaxies that stopped forming stars billions of years before they were supposed to. It also found chemicals in exoplanet skies that do not belong there. If you were hoping for a telescope that would quietly confirm what we already believed, then this is not it. So let's look back. Not at the launch and not at the hype, but at the work, the timeline, and the things it actually found moment by moment. Because the real story of the Webb is not in its design. It is in the discoveries, and some of them still do not make sense. We all saw the image, and it looked like a starry wallpaper. It was nothing more than a tiny dot in the sky magnified 100 times over. But once the shock wore off and people stopped saying pretty, the scientists started digging into the details, and that is when things got interesting. That single image, just one, showed thousands of galaxies. Not stars and not planets, but galaxies. Each one was filled with billions of stars of its own. They were scattered across an area of the sky the size of a grain of sand held at an arm's length. It was called SMACS 0723. It was a massive galaxy cluster located about 4.6 billion light-years away in the constellation of Volans. But honestly, the name did not matter. What mattered was what it proved. For the first time, we had a clear infrared look into the deep universe. And it did not just show distant galaxies. It showed warped, light-lensed arcs and ghostly shapes stretched across space and time. That warping was not an error, it was gravity. The massive clusters in the foreground were bending the light of even more distant galaxies behind them, And those distortions were not just beautiful, they were useful. Gravitational lensing acts like a natural telescope. It magnifies, it reveals, and it lets us peek behind the curtain. So in that first image, we were already looking at galaxies that existed over 13 billion years ago. This was just a few 100 million years after the Big Bang. That alone was impressive. But here is the part that caught everyone off guard. Some of those galaxies looked to be too bright, too structured, and too evolved, and that did not line up. According to most models, galaxies back then were supposed to be small and chaotic. They should have still been forming their first stars. But what the Webb showed even in that first photo was something much further along. It showed smooth structures, defined clusters, and evidence of star formation. This process should have taken hundreds of millions of years, more time than the universe had given them at that point. So naturally, the questions started to pile up. Were these galaxies forming faster than we thought was possible? Were our models of the early universe just wrong? Or were we looking at something else entirely? A different kind of structure built under different rules, and this was just day one. This was before the Webb had even locked in its full calibration. Its instruments had not yet been tested across the board, but it had already sent us back to the drawing board, not because the data was unclear, but because it was too clear. It did not confirm our expectations, it challenged them. What is wild is that this was not some deep survey that took months to complete. It was a snapshot, a glimpse. It was proof that even in the blankest parts of the sky there are entire universes hidden in the dark. They were waiting quiet until the right lens came along. That lens was the James Webb, and in just a few hours, it rewrote our map of the early cosmos. A telescope like the Webb was not built just to stare into the ancient past. It was also designed to look closer, not at galaxies billions of light years away, but at the stars just down the street. These stars are orbiting their own little worlds. These are the worlds we have been chasing for years, guessing their shapes and estimating their temperatures. We have been watching their shadows, and up until now, that is all we really had, the shadows. When a planet passed in front of its star, we would see a tiny dip in light. That is how we found them. That is how we measured them. It worked, but it was limited. You can learn a lot from a silhouette, but it does not tell you what the planet is. It does not tell you what it is made of or what is in its sky or if anything is living there. The Webb changed that. Its infrared sensitivity made it possible for the first time to read the actual chemical fingerprints of an exoplanet's atmosphere. Not indirectly, not through noise and modeling, but directly. It splits the light that passed through it and analyzes the spectrum one wavelength at a time. That is how we got the first clear detection of carbon dioxide on a planet outside our solar system. This was WASP 39b, a hot gas giant 700 light-years away. That one single result proved the concept. It was not just hype anymore. The Webb could read alien atmospheres, and then it went further. The Webb found water vapor on WASP 18b, WASP 80b, and GJ 486b. These are not friendly planets. One of them is boiling, one of them is practically hugging its star. But the point is not that they could host life. The point is that we could read them. We could measure the thickness of their clouds, track the changes in pressure, and see the signs of things like methane and sulfur dioxide. These are gases that mean something when they show up in the right combination. Then there came WASP 17b, and that is where it got weird. The Webb did not just find a vapor or a gas. It found solid particles in the planet's sky. They were tiny silicate crystals, essentially glass, suspended in the atmosphere. The same way Earth's clouds can carry water droplets, this planet was flinging microscopic quartz around like hail. It was the first time we had seen anything like that, and it made us realize something. Exoplanets do not follow Earth's playbook. Their weather systems, their skies, and their entire logic might be different, wildly different. and the Webb was the first tool that could actually show us. But it did not stop with exoplanets. The Webb turned its gaze inward too, toward our own solar system, and even though these were closer targets, it still managed to surprise us. It captured the sharpest view of Neptune in over 30 years. Not just the rings, but the thermal profile, the poles and the cloud tops. The level of detail was unreal. Then it locked onto Chariklo, a strange asteroid with its own tiny ring system, and detected water ice. That is an object that is only a few hundred kilometers wide, yet the Webb could map its surface. Then it turned to Europa, one of Jupiter's moons. It detected plumes of water vapor venting into space. That confirmed what we had suspected from older missions like Galileo and Hubble, but this time it was crystal clear. Europa was not just frozen. It was active, breathing, and jetting out the contents of its subsurface ocean like a leaky faucet, and the Webb was watching it happen in real time. Even Comet 238P, read a small rock in the asteroid belt, got its spotlight. The Webb detected water but no carbon dioxide, which was weird. Most comets have both of them. This one did not. That tells us that maybe this comet was formed in a warmer region than we thought, or perhaps its carbon dioxide has long since escaped. Either way, that is a clue about comet formation, about solar system chemistry, and about how water made its way here in the first place. And then there were the trans-Neptunian objects, the icy bodies way out past Pluto. The Webb started to pick up traces of methanol and organic compounds on them too. This helps us piece together what the outer solar system was like in its earliest days. These were not just static leftovers. They had chemistry change and a history. So yes, the James Webb was built to look far, but it turned out to be just as powerful when it looked near. Because every time it focused on something we thought we understood, it showed us something we had missed. This was true whether it was a planet we had already discovered or a moon we had been circling for decades. In 2023, the JWST started to pour in data from deep field surveys. One of the first things astronomers noticed was the sheer number of galaxies it was picking up. These existed in the first few 100 million years after the Big Bang. They were not just faint blobs of light and not background noise, but fully formed galaxies. First there were dozens, then hundreds in places we thought was still empty space, and some of them were just wrong. Take Ceres 93316 for example. Based on its redshift, it looked like this galaxy existed just 235 million years after the Big Bang. It was the farthest galaxy ever observed at that point. That is way earlier than we had expected anything that complex to exist, and it was not alone. The Webb kept picking up more like it, bright, compact and well-structured galaxies. They did not look like they were still forming. They looked to be done. And that was a problem, because to make a galaxy like that you need time. You need heavy elements. You need stars that live and die and explode and recycle their guts into the next generation. You need dust and gas and rotation and gravity, all working in sync over hundreds of millions of years. But these galaxies did not have that kind of time. So something was not adding up. Were these galaxies somehow forming faster than anything we had ever seen? Were they forming differently, skipping the steps we thought were necessary? Or was our whole timeline for the early universe off by a wide margin? And then the Webb found something even stranger. The JWST Advanced Deep Extragalactic Survey, or JADES, is one of its largest deep field imaging programs. It focuses on the GOODS S and GOODS N fields, offering detailed images of galaxies at high redshifts. These observations were expected to refine our understanding of galaxy formation. They were also expected to clarify how supermassive black holes achieve their enormous masses so early in cosmic history. However, a surprising discovery from JADES' data has challenged fundamental assumptions about the universe's structure. Specifically, it challenged the principle of isotropy. This principle posits that the universe should appear roughly the same in all directions. There should be no preferred orientation or spin. In a study led by Lior Shamir of Kansas State University, researchers analyzed 263 spiral galaxies. They studied the good-south field by using the Ganalizer algorithm. This algorithm assesses a galaxy's spin direction from radial intensity plots. The results revealed a striking asymmetry. 158 galaxies, or 60%, rotated clockwise. Meanwhile, 105 or 40% rotated counterclockwise. This imbalance hints at a possible preferred spin direction in this region of space. This challenges the notion of a directionless, homogeneous universe. Previous studies have noted similar spin asymmetries. The effect appears to be more pronounced at higher redshifts, suggesting a potential primordial structure in the cosmos. Some speculate that this could align with physicist Nikodem Poplawski's unconventional theory. This theory proposes our universe was formed inside a rotating black hole in a parent universe. This could possibly impart a directional spin bias to cosmic structures. However, Shamir's team offers a more conventional explanation. The asymmetry might stem from a Doppler effect bias. The Milky Way's motion could make galaxies spinning opposite to our perspective, clockwise from Earth, appear slightly brighter. This brightness would be due to a blue shift potentially skewing the automated classifications. The small sample size of 263 galaxies and the challenges of imaging faint high redshift objects further urge caution. Larger, more diverse datasets from ongoing JWST observations will be crucial. They will determine whether this asymmetry reflects a true cosmic phenomenon or an observational artifact. Compounding these challenges to cosmological models, JADES has also uncovered galaxies with redshifts exceeding 13. This means they existed when the universe was less than 330 million years old. These galaxies, far from being weak protostructures, are luminous, compact, and surprisingly mature. A standout example is JADE SGS-Z130 with its extreme redshift. It has forced astronomers to reconsider how early galaxies could collapse from primordial gas clouds in such a short time frame. Typically, such collapses require extended periods, yet these galaxies appear fully formed within the universe's first 300 million years. This is not an isolated anomaly, but part of a pattern. These early galaxies were not just existing, they were thriving. They were actively forming stars at ridiculous rates, more stars than they should have been able to form. They did this with the limited ingredients that were available. It was like watching a campfire suddenly erupt into a 5-alarm blaze. But it happened in the vacuum of space before the wood had even dried. Some astronomers started to call it the too early, too big problem. The galaxies were too massive, too luminous, and too soon. So what is going on? One possibility is that star formation in the early universe was simply more efficient than we thought. Maybe the conditions back then, the higher densities, the more frequent collisions, allowed galaxies to grow at warp speed. Or maybe our models are missing some critical ingredient, perhaps a cooling mechanism, a gravitational effect, or something we have not accounted for yet. Another idea is that these galaxies were formed from a direct collapse. Instead of slowly gathering stars and building up mass, maybe some collapsed almost instantly from dense gas clouds. They would have formed stars and black holes in one quick, chaotic event. If that is true, it could explain how some of the earliest quasars came to exist so early too. Quasars are the super bright beacons powered by black holes. But here is the twist. The more we try to explain it, the more complicated it gets. Because every time the Webb stares into those early epochs, it finds more galaxies, not fewer. It finds more light, not less, and more structure when we expected randomness. And now astronomers are facing a deeper question. What if the early universe was never as quiet as we thought? What if everything, The stars, the galaxies, and the black holes came online faster and louder than we have ever imagined. If that is true, then the universe is not just older than we thought. It is busier, more aggressive, and more alive even in its infancy. And all of this, all these findings that broke our timeline, came from just the first year of the Webb's deep fieldwork. We are only scratching the surface. The moment we found galaxies that were too big for their age, another question came up right behind it. If these galaxies are already so massive this early, then where are the black holes that should have grown with them? That has been a long-standing puzzle in astronomy. We know that most large galaxies today have a supermassive black hole at the center. They are sometimes billions of times heavier than our Sun, but we still do not know exactly how they form. Do they start as small ones that slowly eat their way up, or do some of them just appear fully grown? The James Webb did not solve that question, but it gave us something we did not expect. It gave us proof that these monsters were already around in the early universe. One of the biggest surprises came from a galaxy called Sears 1019. It is distant and faint, but when the Webb looked closer, it saw a clear signal. It was the telltale signature of an active galactic nucleus. This means there is a black hole in the center, and it is feeding, not just existing, and not just waiting, but feeding. That is important because Sears 1019 is not in the modern universe. It is from a time when the cosmos was only about 570 million years old. So how did a black hole, even a small one, form, grow, and start to actively pull in matter that early? That is not supposed to happen. Black holes need material, they need mass to form, they need stars to die, and they need galaxies to evolve. And all of that takes time. But this one and a few others like it seem to skip that timeline entirely. They are just there. That led researchers to revisit a controversial idea: direct collapse black holes. The idea is that instead of forming from stars, some black holes might form straight from massive clouds of gas. They would collapse under their own weight before a single star ever shines. It is messy and it is fast, but it might explain how black holes could have been born big, and once they are big, they do not stay quiet. That is where the quasars come in. The Webb began spotting quasars from more than 13 billion light-years away. These are incredibly bright beacons powered by black holes that were gobbling up matter. One of them in a galaxy called J148 plus 0600 was so bright that its luminosity had to be explained by gravitational lensing. A giant galaxy cluster was bending the path of its light across space. That is not just a pretty trick, it is a window into the deep past. Lensing takes objects that would normally be too faint and stretches them out. It magnifies them and gives us access to more detail than we should be able to get. And it works both ways. One of the most striking examples came in September 2023. Astronomers spotted a supernova, a dying star, that had been triply lensed by a galaxy cluster. It was nicknamed SNH-0PE. It appeared in 3 places at once, all of them slightly offset in time. Think of it like a cosmic time delay. The same explosion was playing back through different routes in space. That is more than just fascinating. It is useful. By measuring how long each image takes to appear, astronomers can actually use lensed supernovae to measure the expansion rate of the universe. This is something we have been arguing about for years. There is a whole debate called the Hubble tension. It's the idea that our 2 best ways of measuring the universe's expansion rate give different answers. But lensed supernovae like SNH-0PE offer a third way, and the Webb's sensitivity makes it possible to catch them early, even when they are faint. So while it is out there spotting galaxies and black holes that should not exist yet, it is also quietly helping. It is helping to solve or to complicate one of the biggest cosmological arguments we have. But then the Webb found something even stranger. It started seeing galaxies that were no longer forming stars. not millions of years into the universe's history, but within the first billion years. These were not galaxies that were just starting to wake up. They were already quiet done, as if they had been lit up briefly, burned fast, and then just stopped. That is not supposed to happen either. Galaxies are expected to go through a long, messy adolescence. Stars are forming, dust is flying, and chaos is all around. But these galaxies, found just 700 million years after the Big Bang, were already quiescent. That is the technical term. There were no new stars forming and no gas left to work with. It is like finding an elderly person in a kindergarten classroom. You do not expect to see someone that evolved that early. But the Webb found them multiple times. They are now being called the Sleeping Beauty galaxies. It is a catchy name and a strange reality, because we still do not know why they stopped so early. We do not know if they might wake up again. But it is clear that star formation, just like galaxy growth and black hole birth, does not follow one simple rulebook. For a while, the Webb's discoveries were all about what we did not expect. They were about galaxies that were too soon, black holes that were too big, and stars forming too fast. But in early 2025, something changed. The conversation shifted from structure and timing to life. The target was K2-18b, a planet about 120 light-years away. It was orbiting a cool dwarf star in the constellation of Leo. We had known about it for a few years. Other telescopes had picked up hints that it might have water vapor in its atmosphere. That alone made it interesting. It was not Earth-like, but it was still in what is loosely called the habitable zone. Not too hot, not too cold, just maybe right. But the Webb saw something more. In April 2025, scientists announced they had detected dimethyl sulfide, or DMS, in the planet's atmosphere. On Earth, this molecule is only produced by life, specifically by marine plankton. There are no volcanoes, no lightning, and no chemistry that we know of that makes it without biology. However, scientists caution that unknown abiotic processes could potentially produce DMS. For example, photochemical reactions in hydrogen-rich atmospheres could be a cause. Now, it is important to be cautious here. This is not a confirmation of aliens. It is not proof of anything. The signal is not strong enough yet to be called a detection beyond all doubt. But the odds, they are high enough to pay attention. Some estimates put the confidence at around 99.7%. That is not a certainty, but not noise either. The Webb did not just pick up DMS. It also spotted methane, carbon dioxide, and hints of dimethyl disulfide. All of these are molecules that in the right mix could point toward biological processes. And K2-18b is not a gas giant. It is what we call a Hycean world. It's somewhere between a super-Earth and a mini-Neptune. It's a water-rich planet with a thick atmosphere, possibly with a global ocean under the clouds. That combination, water, methane, carbon dioxide, and DMS, is strange. It is not impossible in theory, but it is very unlikely without something living in the mix. Of course, people debate it, and they still are. Could photochemistry do this? Could there be some exotic process that we do not understand yet? Possibly. But that is what makes the observation important. It raises a real testable question. And it is the first time we have ever had that from a planet outside our solar system. There is no artist's impression, no theory, just data. And while the headlines ran with it, sign of life, the real value is quieter. The Webb is finally giving us what we need: clues, not stories, and signals, not speculation. But that was not the only milestone the Webb had crossed. In May 2025, astronomers confirmed the detection of the most distant galaxy ever seen. It was a compact, bright object named JADESGSZ140. Its redshift was calculated at a Z of approximately 14.32. This means the light left it over 13.5 billion years ago. At that time, the universe was just 290 million years old. Let that sink in. We are now looking at galaxies that existed when the cosmos was less than 2% of its current age. JADES Z140 is not a massive system like the Milky Way. It is small, intense, and bursting with star formation. But it is real, and it is not alone. The Webb's deep field work has identified dozens of similar candidates. It is slowly filling in the blanks of a time we have never truly seen before. Then there came one of the strangest visual surprises in recent memory. In July 2025, the James Webb Space Telescope captured an extraordinary image of two galaxies caught in a mid-collision. They formed a system that was dubbed the Infinity Galaxy. When it was processed and sharpened, the combined shape resembled a near-perfect infinity symbol. It was a figure-eight twist of stars, gas, and gravity. The astronomers were captivated by its striking appearance, but the real story lay deeper. Now, yes, the shape got attention. It is striking, but the real story was not the symbol. It was what was hiding inside. At the heart of the collision between the two galactic nuclei, researchers identified a supermassive black hole. It was actively feeding, pulling in material, and building mass. Based on its brightness, its energy output, and the extreme gas density of the collision, there is a compelling possibility. This may be a direct collapse black hole. This is a rare phenomenon where a massive gas cloud collapses directly into a black hole without forming stars. This could be a critical clue to one of astrophysics' biggest mysteries. That mystery is how supermassive black holes grow from nothing to giants in a relatively short time. The Infinity Galaxy was observed about 7.5 billion years ago. The universe was roughly 6.3 billion years old at that time. It is not from the earliest cosmic epochs, but it offers a vivid snapshot of the chaotic merges that shape galaxies. These merges also shape their central black holes. More than a stunning image, it serves as a laboratory for studying the processes that drive formation. It helps us study the formation of the universe's most massive objects. It illuminates how collisions and extreme environments can spark the rapid growth of black holes. We have been detecting exoplanets for nearly 3 decades now. In all that time, we have mostly done it by inference. We watch how starlight dims, shifts, or gets distorted by something passing in front of it. It is effective, but it has never really felt like seeing a planet. It is more like watching a shadow dance and trying to guess what had cast it. So when the James Webb Space Telescope captured its first direct image of an exoplanet, it was not just a milestone, it was a moment of clarity. It happened in September 2022. The planet HIP 65426b had not even been the focus of any headlines before. It was one of the quieter targets, orbiting a faint star about 350 light-years away. It was not Earth-like and not habitable. It was just a massive gas giant several times the mass of Jupiter. This is the kind of planet that is easier to image because it is big, bright in the infrared, and sits far from its star. This way it is not drowned in glare. But that is exactly what made it the perfect test case. By using its coronagraph, a device designed to block out a star's blinding light, the Webb was able to isolate the faint glow of the planet itself. It was not a shadow and not a spectral trace. It was actual light coming from the planet's atmosphere, captured and analyzed in detail. That light revealed a temperature, a cloud composition, and molecular fingerprints. It confirmed methane-detected water vapor and even suggested deeper structures in the cloud layers. It suggested things like pressure systems and haze, and for the first time, scientists could study a planet in another solar system as a world with its own visible character. It was not just a line on a graph. Of course, this kind of direct imaging is not new in theory. A few ground-based telescopes have managed to do it under very specific conditions. But those images were faint, noisy, and barely enough to tell you what you were looking at. This one was different. This was clean, high resolution, and detailed enough to break down what the atmosphere was doing. It showed not just what it contained. It was the first time the distant glow of a world outside our solar system could be treated like real data, not a suggestion. And now that the Webb has proven it can do that, the possibilities just opened up. Planets like HR 8000, 799c Beta Pictoris b, and eventually the smaller, cooler ones are now within reach. These are the ones we really want to understand. We can reach them slowly, carefully, but for the first time visibly. And again, this was not hype. There was no big countdown and no splashy press event. The data was released through peer-reviewed studies. And the image, while simple, carried all the weight of the 2 decades of engineering behind it. This is how major progress happens now. Quiet, technical, measured, but undeniable. And while the Webb was doing that, it also turned its attention to things much closer. These were things flying through our own neighborhood, like the asteroid 2024 YR4. This was a near-Earth object about the size of a 15-story building. It was not a headline grabber and not a threat, but still worth studying. This is because small, fast-moving asteroids are hard to observe with traditional telescopes. They move quickly, reflect very little light, and often slip past with only a brief window of visibility. But the Webb caught it, tracked, it measured its surface composition, and determined its exact orbital characteristics. It even helped to refine the risk models for the Moon, which had a low probability impact window. This was due to gravitational interaction. It was not flashy, but it mattered because it showed that the JWST is not just good at looking into the past. It is good at looking around, at scanning the space near us, with more detail than any telescope has ever had. It can do this even when the object is small, dim, and moving fast. And that is part of the real story here. Everyone thinks of the Webb as the deep universe machine, and it is. But its infrared sensitivity, its precision tracking, and its spectral resolution have made it useful for everything. It is useful for icy moons, dusty comets, active asteroids, and beyond. It is not a one-trick telescope. It is a toolbox. And the things it is helping to answer, from atmospheric chemistry to orbital dynamics, are not separate. They are connected. Because if we want to understand how common Earth-like worlds might be, or how life could survive in harsh conditions, we need all of it. We need to know what the early planets even looked like. Not just the distant galaxies, and not just the biosignatures, but the full picture. From here to the edge of what we can see. By now it is obvious that the James Webb is not just another space telescope. It is not a sequel to the Hubble. It is not a mirror in the sky that happens to see a bit further. It is something else entirely, something that is quietly reshaping how we understand the universe. It is not doing this by screaming headlines or dramatic discoveries. Instead, it is collecting the kind of data that changes everything over time. That change is not always loud. Most of the time, it is just a shift in what questions we are even allowed to ask. Now, before the Webb, we had guesses about the early universe. Now we have measurements. Before the Webb, we could detect an exoplanet. Now we can describe its weather. Before the Webb, we thought that galaxies took their time. Now we have seen them form, burn out, and fade, all within the first billion years. And that is the shift not just in what we know, but in how we think about what is possible. Because what this telescope has shown over and over is that the universe did not evolve slowly and predictably. It evolved fast, and sometimes violently. The galaxies grew faster than we thought they could. The black holes did not wait their turn, and the stars were formed, burned out, and passed the torch long before we were supposed to be able to see them. And yet, there they are, as clear as day, sitting in the Webb's data. So now we are left in an unusual place. We are in a place where some of the biggest answers have raised even bigger questions. Why were so many galaxies already mature when they should not have had time? How did black holes appear so early, and what made them feed so fast? What kind of worlds are out there that could carry not just water and clouds, but chemicals we have only ever seen here on Earth? And maybe the most honest question of all, how much of our understanding was built on models that were just too neat? How much was built on models that were too slow and too simplified? The web is not here to confirm what we thought. It is here to challenge it, to test it, and to make sure we are not just building stories that feel right. It ensures we are building ones that match what is actually out there. And it is still early. There are thousands of observations in the pipeline that have not even been made public yet. There are entire surveys that will run for years. And there are missions planned to pair the web's results with new instruments. These will look in other wavelengths or catch up in resolution. And then there are the things we have not even imagined yet. The surprises, the quiet anomalies, the strange patterns in the background galaxies, the leftover questions from redshift measurements that do not quite align, the weird atmospheres, the gaps in stellar mass, and the lensed flashes that might be something more. Because the thing about a telescope like this is that you never really know what matters until you look, and when you finally do it is never what you expect. No one knew the Webb would find galaxies that shut down before they even got started. No one guessed we would get hints of life from a planet 120 light-years away this soon. And no one expected such clear detail from the farthest galaxy ever seen to the clouds on a gas giant right next door. But that is what it is doing. Not once, and not occasionally, but constantly. And in doing that, the Webb has quietly shifted astronomy. It shifted it from a field based on hopeful estimation to one grounded in evidence, detail, and sometimes uncomfortable clarity. It is not about the pretty pictures. It is about finally seeing what is real. And if this is what the first 3 years look like, then the next decade is not just exciting, it is going to change everything.